recording has started. Okay, unfortunately I wasn't able to find a way to share the document camera I'm looking at, but I'll do my best to say, I'm looking at answer D or whatever. So let me start the screen and sharing the screen and myself. This one, go live. And then I'll also share my video if that helps any. Okay. Okay, starting on question 5. If you see the screen right here, the link will be in the description of the video if you're watching it. It's the University of Illinois Chicago Quantum Computing Club Qiskit Certification Study Guide. So again, in the description of the video, if you're watching it on YouTube, and we'll be looking at the link that says Manny Gomez, old notes, wrong answer, rationale. So we're going to click that. That's what we're looking at. Here it is. I'm going to go here, download it, and then open it up. We are on question 5. So download, open. Okay. We are on this one. Okay, now I'm going to switch to the document camera so that we can see as I point. Press this. Turning it on might help. Okay. Nice, okay, so I'll get the light going. I think this is Zoom. Let's see here. Okay, still able to be seen. Autofocus. There we go. Okay. Okay, question 5. Which code fragment will produce a maximally entangled or Bell state? Okay, this question is your friend. When you see this mentioned, you should start smiling because on the right side you can see here I've written the only thing that's required. So what first thing first? What is a Bell state? It is just a state that has higher stability than other ones. So people found these states and they gave them a name, so they're called Bell states. So all you need to construct a Bell state is a Hadamard and a CNOT gate in that order. So here we see on the right, Hadamard and then CNOT required to create a Bell state. And then some other information about Bell states that might come up later. 0.707. So there's these things called state vectors, which is a way, it's a form of visualization that gives you more information on a state. So if you see 0.707, there's a good chance that what they're talking about is a Bell state as well. But for this question, all we need to know is right here, Hadamard and then CNOT is required to create a Bell state. So what we're going to do, knowing that, is go through all of them and just see which one has a Hadamard and a CNOT in that order. They don't necessarily have to come one after another sequentially. It's just as long as there's a Hadamard and then some point afterward, there's a CNOT, you got it. Okay, so we're going to go bottom to top. Okay, looking at D, they set up the circuit. It's a Hadamard and a Hadamard. That's not a Hadamard and then a CNOT. That's not what we need. So here we have D that says 2 Hadamards, criteria not met. Okay, going one up. A Hadamard, oh, okay, an X and a CNOT. So it's a control Z, a 0 control Z. So that's not a Hadamard and a CNOT. It's close, CZ instead of CX, but it's not there. So control Z, not part of Bell states. We look at option B. Let's see here, CX and then an H. So we have CNOT and then H. The right parts are there, but not in the order we want. So let's see here. We says CNOT and then a Hadamard is for, it's for decoding entangled info. So now we have some more context. If you do a Hadamard and then a CNOT, that is what's used for encoding information. But then if you flip them, that is how we decode and bring the information back. So B gives us more context for that. And now I'm guessing A, I'm not looking at it right now, but I'm guessing at some point there's a Hadamard. Maybe there's some stuff in between, but then there's a CNOT. Let's see here. A Hadamard, some stuff in between, and then a CNOT gate. So that's why A is our answer. Again, try to recognize the patterns of the test. You know, what's needed for a Bell state, a Hadamard, and then a CNOT. Question 6. Let me see here, 1 second. Okay. Given this code, okay, you can see all of it. Given this code, which two inserted code fragments result in the state vector represented by this Bloch sphere? Okay, so this question, some background information might be useful. So if you want to learn more about Bloch spheres, which I really recommend you do, and how gates interact with them, I've mentioned this, I think it was question 1 and 2, or 2 and 3, but at some point I mentioned it before. I'm going to switch back to my computer screen. I recommend looking at, there we go, and Googling, let's see here. So let's see if it's on our main hub document. Let's see here. We have the CERT announcement, we have the advice doc posted by IBM, 20-second sample questions, that's what we're going over right now. 60-question sample test, what I recommend taking. Qiskit textbook, operations glossary. Oh, I don't have it on here. Okay, that's good to know. I'll add it right now. But you want to Google Grok Bloch. Hopefully you can see the spelling there. Cool. And it's in orange because I've been there a bunch of times. James Weaver made this. Great guy. He's in charge of the Qiskit Slack currently. So here it says, use it. You can run it online, demo. So click this, and it gives you, let me go back to read the description. Is there an info about what it's used for? README. Here we go. An application that helps users understand the Bloch sphere. So I'll go here, run the demo online. And then again, I recommend going through with this and, you know, figuring out what each gate does. So an X gate, you know, depending on where you start, an X gate will do a certain thing. So here we go from 0 to 1. And then they each have different, you know, properties. So starting from 0, you can always refresh it as well if you want to go back pretty easily. So I'll go back to the document camera to add some context. On the right side, we have a note, on the left side, sorry. We have a note, and it says, it's like settings, it's supposed to be SI. I was like, what is this? It's like sitting at the top and just letting it fall down the axis of rotation. So I don't know how well the camera will pick it up, but if we're looking at, if we imagine a Bloch sphere here facing in front of me, so toward you is the X direction. If we're looking for a rotation along the Y direction, if X is this way and this is Y, and there's a rotation along the Y axis, what you do is put your elbow on the axis and let it fall as if it's swinging like a metal rod. And this is the Y-axis. If I put this here, eventually it'll fall either this way or it'll fall this way. And then to turn it, you know, it'll fall either this way or this way. That's the Y-axis. So X-axis, same thing, except it'll fall this way or this way. So X-axis falls, you just put it at the top, you sit it at the top and let it fall. And the elbow is sitting on the axis itself. So, again, approaches for these questions. How do you approach it? How do you think? What should you do to maximize your time? I do not look at this part first. After a bunch of studying, I learned that they don't try to trick you. You don't have to look at this first. You could complete this question without looking at this part, actually. Maybe we should do that. We should just to prove a point. I'll put this here. How well does that work? Whatever. We can imagine, ooh, I forgot there's a mic there. We can imagine something is covering this. So it's not needed. So looking at the answer options, we go down and we see, starting from the bottom, because that's just how I like to do it. Just not worth it. Whatever, we know we don't have to look at it. So E, a rotation on the y-axis, so QC.ry. R stands for rotation on the y-axis. And it's a distance of pi. So that would be like going from state 0 to state 1. Because the horizontal axis, the middle part, this right here is pi over 2, this middle part. And I'll trace it in red. Pi over 2. Very important to know that. If you go back, we explain more in example 2, how to think of it. Again, we see pi over 2 and other references. So E, it says here, it would land you at the base. So right here in this purple point, and you can follow the colors to see where each point corresponds. But a rotation along the y-axis for a quantity of pi would land you from state 0 to state 1. And a rotation on the x-axis of the same amount would do the same thing. You just take a different route to get to the same place. So if you did it with the y, it would go start here, and it would go down, 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 down to 1. Now, if you did it for the x, at a distance of pi, it would take this route, but still land you at 1. So y-axis is this direction and this direction. Positive y is this direction, negative y is this direction. And x-axis, positive x is this direction, and negative x is this direction. And then z is a combination of both, but that's something else. Okay, so it's not E, because it would land you at pi, because it's a whole pi. And it's a little covered by all the drawings I have, but it says, given this code, which two inserted code fragments would result in the state vector represented by this Bloch sphere? You can't really see it, but it's given. It comes with the picture. It's just drawn over right now. There is a red arrow right here. And I'll try to make it a deeper red, because there's lines over it from my old notes. But that's the state we want. So this is a pi over 2 distance. And we could also achieve, maybe I shouldn't say this because I'm skipping ahead a bit, but that is the state we would get if we use a Hadamard gate. And if going back to this Groch sphere, or Groch block rather, we can see that we start at 0, and it's always assumed you start in this position right here on the screen. And if we apply a Hadamard gate, it puts us in that state. And if we apply another Hadamard gate, it maybe it's too technical of a term, and maybe it's incorrect, but it negates it almost. So one puts you there, and another brings you back. Maybe negate is too technical of a term. I don't know if it technically negates it, but one brings you there, and the other brings you back. So going back to the document camera. So that is what we're probably looking for in this question. But there are different routes to get there too. You can go down the x-axis and then use an S-gate, which I'll show here. But just don't get too hard set on thinking there's only one solution. So if we started here, used an x of pi over 2. So this has increments of pi over 6, I think. 1, 2, 3, 4, whatever increment that is. So if we did an x rotation of pi over 2 and then did an S-gate, we'd also get there. So there are many routes to get to the same point, so don't get stuck thinking that there's only one way. So that's why I recommend playing with this Groch block, because you as you just saw, like I found some other paths to get to the same end result. So, the easy answer would be a Hadamard, and if there's a solution here that says Hadamard, we know it's that, but we have to keep our mind open. So E is incorrect because it's a full distance of a full pi, so we just send you straight from here all the way to the bottom. Okay, now D. We have a rotation on the x-axis. How well can you see my pen pointer? Good. We have a rotation on the x-axis of a distance of pi over 2. Okay, so that's good. So we have the first half of that example I just showed, because we pi over 2 on x. Now, if the next step was an S-gate, we'd be set, but let's see. The next step is a z rotation in the negative pi direction. So that would bring us, let's see here, negative pi over 2 direction. So we go start here, rx, a rotation on the x-axis of a distance pi over 2 would bring us from here, here to this point. And then the next step, a rotation in the z-axis of a distance of negative pi over 2 would bring us here. So this is positive rz, this direction, and this is negative rz. So that's incorrect. D would land you here. The orange, leads us there. Okay, C, and again we have to keep in mind this question says which 2 code fragments results in the state vector. So 2 answers. C we know is correct because I did it ahead of time. So let's skip over it and go to B. We have a rotation in the x-axis of a distance of pi over 2. Oh, it's the first step of our part D. So again, we know it's rotation x-axis, or distance of pi over 2. Here, lands us here. So that's incorrect. Okay, so now A and C, we know they're correct, but why are they correct? Let's take a look at them. A is the easiest to explain. Like we saw, you can get to that state with one Hadamard gate. And that's what we see there. They use one Hadamard gate and they get there straight away. So it's a nice clean answer. But again, there are different routes to get to the same position. Let's look at C. Okay, it's a rotation on the y-axis of a distance of pi over 2. So we start here, and again, this is the axis that we're putting our elbow on. So it's like this. Okay, now transferring that into real life, it's like this with the y here, and we let it drop. Let it drop. It's a little hard because the elbow, but y-axis, let it drop. So positive, pi over 2 would be this y-axis here, let it drop here. And that's where we want to be. So that's why C is correct. So question 6, main points, practice with the Bloch block. There are multiple ways to get to a position on a Bloch sphere. And I'd say just practice. You learn, some funky stuff happens with S gates sometimes. There are cool interactions that happen. And I'd say sometimes the S gates would be one that tripped me up. So if you're gonna maybe look at some niche fringe cases, it might be the S gates that you might need to focus on. Speaking of S gates, question 7. This one's a pretty straightforward one. It's just about knowing the gates. So before we tackle this, I really recommend, I think it's actually already on the hub document. Hold on, let me add the link to the Bloch block to the hub document, just so I remember for later. Okay. I really recommend for question 7, it says S gate is a Qiskit phase gate with what value of the phase parameter. So for these things, I recommend going to this link. It's called the operations glossary. Clicking here. This is the bottleneck that I really recommend you study on because it's what Qiskit is capable of. It's a short, sweet document. Once I found it, I was like, they need to advertise this document a lot more than what they're doing because it's a very important one. And it's a very short one, which is great. It says overview. This is pretty much, these are what we are working with. Classical gates, phase gates, these operators, this thing, Hadamard gate, quantum gates. But what you see right now on the screen is what you need to learn practically. It's looking at this, and they're colorful like Skittles, so maybe that's part of it. But it makes it easy to digest. There's not a crazy stuff of quantum, math, and that's there in the background. But what you need to learn is this, what you see on the screen. So again, what we see is the question asks about phase gates. So what you want to go through, I would show my notes. Maybe I'll bring them next time. Of me, how I went through this. But click here, brings you to the phase gate, and it gives you the information on it. So once you learn this, certain gates have their properties. So, 2 S's equals something else. Maybe if I'm remembering correctly, two T gates equals an S gate. That might be backwards, but it's something like that. So S gate right here says the S gate applies a phase of I to the one state. This is just more background information. It is equivalent to a Z rotation for the angle of pi over 2. So here we see this pi over 2 is associated with the S gate. This is what we need. That ends up being the answer for the question. But S gate is pi over 2. T gate is pi over 4. So 2 T gates, so a pi over 4 plus a pi over 4 is 2 pi over 4, which simplifies to pi over 2. So 2 T gates equals 1 S gate. And I think it might be on this exam, but sometimes they have questions like that where they try to trick you up and they're like, what's the equivalent circuit of this? And that's the logic they use. So again, going back to this hub document, I recommend looking at the operations glossary. I'll make sure to bring mine next time, or at some point we can go through that. Maybe that'll be the next thing we go through after looking at this exam. I'll have to think. But I recommend looking at this, and this is where you get the properties of the gates. So like these S gates and T gates are children to the Z gate. The Z gate is a general gate, and that's why this is equivalent to a Z gate for this angle. So they're like specialized gates. So once I have little diagrams I made that help understand, because it seems like a lot at first, but they're all related somehow, and they're like it's like a mother gate to the daughter gates. But we'll cover that later. So looking at this S gate operations glossary, we see it has the angle of pi over 2. And going back to our document camera, I didn't even fill out C and D because it's like, what do you put? They're not even real gates, so I don't know what I would put. Just say this is not an S gate over and over again. So D is just not an S gate. That's not the property of an S gate. C, it's not, right? So we know the property we're looking for is S is pi over 2. T is pi over 4. So S pi over 2. This B is our answer, pi over 2. And then A is pi over 4, and I say the reason that's not the correct answer is because they're actually describing a different gate. Pi over 4 is a T gate, which is the same thing as saying an RZ of pi over 4. So I'll bring my work in, the drawings I made with the diagrams, but like T gates and S gates are types of Z gates. So it's like a family. So these are types of these. So you can keep going up the chain, and eventually once you go up the highest point of the chain, it's called a U3 gate. It's called a universal gate. So you can just input, that's what I like about the U gates. It's like you input the angle, the distance, and then the phase. And it's a universal gate, so it just has 3 inputs. So starting from the universal, you can kind of create all the other gates. So that's what we'll go over today. Let me just make sure if there's any questions in the chat. If there's any, I'll give about 10 seconds or so, or 15 seconds, whatever, to see if there's any questions. And then if there's not, that would be it for today. Today we went over questions 5, 6, and 7 of the Qiskit developer exam sample questions for exam prep. Again, the link to the main document, the hub document, will be in the description of this video on YouTube. And I'll upload it later today and make sure to post the link to the Discord chat. I see someone's typing, so I'll let them finish out that. Other than that, thank you, appreciate it. Yeah, you too. You have a nice one. That's it for today. Forgot to mention, I'll make sure to add this onto the recording. New advisor for the club, Professor Searles. I wanted to, because I'm recording this because I'm an advocate for I'm a firm believer in the certification program, the certificate and the stuff it teaches. And I think to add on to that, I approached Professor Searles. He's new to UIC, but he's the professor of the quantum information course that's being taught now. And I looked at the course description, and it matches up 1-to-1 of the Qiskit certification exam. I was like, oh, this stuff is perfect for my career. And I asked him for permission to take the class because I didn't have the prerequisites. And I was like, hey, this stuff would be great for my career. And he responded. He was like, after looking at the certification and the stuff you learn from it, this class would just be a review for you. So for anyone wondering about whether the certification is worth it or something along those lines, this just reaffirms that I think it's worth it. And I think having asked the professor that teaches the class on quantum information and quantum computing, he agreed that the class would just be a review for me after having learned what I studied for the certification. So again, just another point for me recommending the certification, and then you guys will most likely see more Professor Schroll's as he transfers over to UIC. He's like in a moving phase, but thank you.